In this lecture, I want to discuss magnetic fields in matter. It's similar to what we did with electric fields. And so what we're going to be doing is we're going to be looking at basically external magnetic fields that are applied to materials. But all materials in the universe are made up of some sort of atom, and those atoms have charges like the proton and the electron. Since the proton is 2,000 times more massive than the electron, then we pretty much put the proton to be stationary, and the electron now is orbiting the nucleus. And in a classical picture, what you would have is you would have the positive nucleus and the negative electron, and it would be in this solar system type orbit. So we're going to basically ignore any kind of quantum effects and treat this classically. So we're going to be treating it as if it was in the 19th century, or actually probably the start of the 20th century, because atomic theory really wasn't formalized until the 19-teens. But anyway, we're going to be treating it like a classical solar system of one charge, a discrete point-like charge, in a closed orbit around the nucleus. Okay. So then so we're going to be now considering a single atom like this, and then we're going to put a magnetic field across that atom, like so. Okay. Now, it should interact because you have a moving charge, and so we can think of the electron as a current. And so now we've got a closed current loop and a magnetic field applied to a closed current loop. And so then there should be a force applied to it, and that force will try and tilt or align the orbit with the magnetic field. So it turns out there are three types of alignment that you can get. The first one being paramagnets, where the dipole moment of the current, so in this case our electron is going to be producing, let's say, a dipole moment in this direction. So that dipole moment is parallel to the external magnetic field. Okay, the second type is called diamagnets. And now the dipole moment is anti-parallel to the external magnetic field. And then the third type is ferromagnets, where these dipole moments remain aligned after the external magnetic field is removed. Okay, so let me see if I can draw a picture of these three cases. And so for paramagnets, you have the orbiting electron producing a magnetic moment, and then the external field is going to be parallel to it. For diamagnets, I could draw the same magnetic moment, but now the magnetic field is anti-parallel. So the two vectors are parallel, they're just pointing in opposite directions. And then for the ferromagnets, I would have all of these dipoles, which now all get lined up once you have an external magnetic field. But once I remove that external magnetic field, they stay lined up, like so. In materials that are not ferromagnetic, if I remove that external magnetic field, then I would get just random alignment, like so. Okay. Okay, so why don't we now try and calculate what the torque would be from an external magnetic field on a magnetic dipole. So in this case, I have my current loop, like this. Current is flowing in this direction. I can draw out my coordinate system, like this. The magnetic moment is going to be pointing in this direction. Let's say, just to make life easier, we'll let the magnetic field be pointed in the z direction. And lastly, the length of these is b on one side and a on the other. The other thing I can point out is that since I've put the magnetic field along the z direction, then the angle between the magnetic moment and the b field is theta. Yeah, okay. So if I took a side view of this loop, then what I would have is, this is the z direction, this is the y direction, this is my wire loop, and I would have magnetic moment, in this case pointing perpendicular to the loop, or in the direction of the area vector. I would have this angle theta, which also turns out to be the theta between the y-axis and the loop. And I would get forces, magnetic forces, of the current and the magnetic field, which would be pointing in these directions. So these forces are the ones that are going to cause it to start to rotate around, like so. So essentially we're rotating the length B around the length A. Okay. So now if I write out the torque is the length A times F times the sine of theta in the x direction. The force, the magnitude of it is, at least, is the current times the length times the strength of the magnetic field. And so if I put that all together, I get the torque is the current times A times B times the magnetic field times the sine of theta in the x direction, or the current times the area times the magnetic field times the sine. Now a current times an area is the magnetic dipole moment. And so the torque I can now rewrite as mb sine theta in the x direction, or the magnetic moment crossed into the magnetic field. And this is a similar result to what we got when we looked at the electric dipole. So for the electric case, the torque that was applied was the electric dipole moment crossed into the electric field. So it's essentially the same thing, same formula. You're taking a magnetic moment and you're crossing it into the field, whether it's electric or magnetic. And so this is an example of paramagnetism, where we are basically rotating the wire loop until M is in the direction of B. So here's our wire loop. Here's the magnetic field. Here's the magnetic moment. And it's going to keep rotating until this magnetic moment is pointing in the direction of the magnetic field. Once they're pointing in the same direction, then there isn't any torque applied anymore. And this is essentially how an electric motor works, except for the fact that when you do get the electric motor, that loop spinning, it does have a forward momentum, and so while the torque is going to rotate it around, the momentum of the loop is going to keep it spinning, so now it doesn't just stop when the magnetic field and dipole moment line up. It should spin a little bit, then the dipole moment and the magnetic field are not going to be lined up anymore. The torque will be applied, and it'll keep kind of spinning around and around and around. Okay. Yeah. So the author of the book goes into a discussion about how this is really easy way to view this is with magnets, because magnets have a north and a south pole. They have a dipole moment, and so you can see how when you put them inside of an external magnetic field, then it's going to cause it to rotate around. Now, of course, the fundamental unit of magnetic charge essentially is not a magnet, but it is a current loop. And so, I don't know which picture is easier for you to kind of remember, either thinking of it as rotating magnets or thinking of it as these wire loops, these current loops that have a specific shape, and then they're just spinning around some axis. Okay, so in the next lecture what we'll do is we'll go over the effects now on the atom, so not just a generalized current loop, but let's look at the electron as the loop orbiting and see what its effect will be on the magnetism.